Hi dear students, this is the second part of the fourth module, that is the reciprocating pump. So in the first part we have gone through the working of reciprocating pump, and we have seen the expression for, we have derived the expression for work done and power, and also we have discussed about the ideal indicator diagram of the reciprocating pump. Now the next topic is, sometimes the question may come like this, show that the work done is proportional to the area under the indicator diagram. As I have explained in the earlier slide, you can see the area of the indicator diagram is nothing but stroke length into HS plus HD. You can see the indicator diagram. Here you can see the area is nothing but area of this rectangle. That means this breadth into this height. Breadth is nothing but stroke length and height is HS plus HD. So area of the indicator diagram is directly proportional to L into stroke length L into HS plus HD. And also we have derived the expression for work done per second as rho G ALN by 60. So in this equation you can see that rho is constant, G is constant, area of the piston is going to be a constant since it is fixed one, and if the pump is running at a constant speed, N by 60 is also a constant. So we can say that the work done per second is directly proportional to A into HS plus HD. So what we have seen now is the area of the indicator diagram is directly proportional to L into HS plus HD, and also the work done per second of the reciprocating pump is also proportional to L into HS plus HD. Since the right hand sides are equal, L into HS plus HD, we can say that the left hand side, that is area of the indicator diagram, is directly proportional to the work done per second. So this is the proof required to prove that the work done is proportional to the area under the indicator diagram. Now we will move on to the next topic, that is double acting reciprocating pump. We have to find out work done and discharge and expression for the discharge and work done of a double acting reciprocating pump. Now before moving into the expression for discharge and work done, we have to see what is happening inside a double acting reciprocating pump. Double acting reciprocating pump is nothing but the water will be acting both sides of the piston of the reciprocating pump. That is, as the piston moves from left extreme position to right extreme position, you can see at the left side of the piston, that is this side of the piston, there will be a suction. Assume that initially there was fluid in the right side of the piston. So when the piston moves backward, that is from left to right, to the left of the piston, suction will be taking place. Correspondingly, if water is there on the right side, by this side of the piston, the water is pumped through the discharge pipe. So one side suction is taking place, through the other side discharge will be taking place. So during the next half revolution, so piston moving from left to right means half the revolution is completed. Theta is 0 degree to 180 degree. So during the next half revolution, that is crank rotates from 180 degree to 360 degree. What happens is piston will be moving from right to left position. So in that time, what happens is through the right side of the piston, that is through this side of the piston, suction will be taking place. Through the other side, the water already sucked during the first half of the revolution will be pumping through the delivery side. So during the one revolution of the crank, two discharge will be there. So that is, during the first half revolution, left side suction will be taking place, through the right side the delivery will be there. And during the next half revolution of the crank, what is happening is through the left side delivery will be there, through left side suction will be taking place. So within a crank revolution, we can almost double the discharge of the pump. That is the advantage of double acting reciprocating pump. Now we have to derive the expression for discharge and work done. So for that, let D equal to diameter of the piston and small d diameter of the connecting rod. See here, this is the piston. D means this is the diameter of the piston, this diameter, and small d the diameter of this connecting rod. This one is the connecting rod. This one is the connecting rod. So diameter of this connecting rod is small d. Now area on one side of the piston, that is on the left side of the piston, area is nothing but pi by 4 capital D square, since diameter of the piston is capital D. So area on the left side of the piston is pi by 4 capital D square. Area on the other side of the piston, that is right side of the piston, since a cross sectional area, a small cross sectional area of the connecting rod is subtracted from the total cross sectional area of the piston in the right side. So area on the other side of the piston A1 will be equal to pi by 4 capital D square minus pi by 4 small d square. That is, together we can write pi by 4 into capital D square minus small d square. That will be the total area on the right side. Now volume of water delivered in one revolution of the crank. So during the one revolution of the crank, as I told, during one revolution two discharge will be there, one from the left side and other from the right side. The discharge from the left side is area of the piston into length of the stroke, A into length of stroke, and from the right side the total discharge will be A1 into length of stroke. A1 is nothing but pi by 4 capital D square minus small d square. Now since length of stroke is constant, we can write as A plus A1 into length of stroke, that is equal to pi by 4 d square plus pi by 4 d square minus small d square into L. That is the expression for volume of water delivered in one revolution of the crank. As we have seen in the earlier case, now discharge of the pump per second is volume of water delivered in one revolution of the crank multiplied by number of revolutions per second. So this will become, discharge per second will become pi by 4 d square plus pi by 4 capital D square minus small d square into L into n by 60. N by 60 is nothing but the number of revolution per second, as I have explained in the first part. Now weight of the water delivered per second, W will be equal to rho into G into discharge per second, that is Q. So that will be equal to rho into G into Q. Expression for Q was pi by 4 d square plus pi by 4 d square minus small d square into L into n by 60. Now work done per second is weight of water delivered per second into total height to which the water is lifted. So the water is lifted through a total height of Hs plus Hd. So weight of water delivered per second into Hs plus Hd will give the work done per second. That's equal to, expression is rho into G into pi by 4 capital D square plus pi by 4 capital D square minus small d square into L into n by 60 into Hs plus Hd. That is the entire equation to calculate the work done per second for a double acting reciprocating pump. See, pi by 4 capital D square is A and pi by 4 capital D square minus small d square by 4 is A1. So in a short form you can remember it as rho into G into A plus A1 into L into n by 60 into Hs plus Hd. Now this is the general equation. In the problems and all, this equation we will be using. If small d is given, then we have to calculate the discharge and work done per second using this equation only. If in some cases in the numerical problems d will not be given, in that case we can neglect the value of the d. So the reason is, if d is very small compared to capital D, then small d can be neglected. So what happens to these two equations, discharge equation and work done per second equation, when d is neglected? You can see discharge per second Q is equal to, initially the equation was discharge per second Q is equal to pi by 4 capital D square plus pi by 4 capital D square minus small d square into L into n by 60. That was the equation. This small d square in this equation is neglected, that is removed. That means the equation becomes pi by 4 capital D square plus pi by 4 capital D square into L into n by 60. That is 2 times pi by 4 capital D square into L into n by 60. That is what is shown here. Q is equal to 2 into pi by 4 D square into L into n by 60. That is pi by 4 d square is the capital A or area of the piston. So 2 times into area into L into n by 60, 2 ALN by 60. Remember, in the single acting case, the discharge equation was ALN by 60. Here you just simply multiplying by a 2, the total the discharge will get the discharge for the double acting pump. So Q of the double acting pump is AL2 into ALN by 60, where in the case of single acting pump it was ALN by 60. Now the same equation, we have seen that work done per second for the double acting pump, considering the connecting rod, piston rod diameter is rho into G into pi by 4 capital D square plus pi by 4 capital D square minus small d square by 4 into L into n by 60 into Hs plus Hd. In that equation, if you remove that d square term, then again what happens is rho into G into pi by 4 d square plus pi by 4 d square. 2 into pi by 4 d square comes there. So again it comes as 2a. So rho into G into 2a into L into n by 60 into Hs plus HD. So the general equation is rho g into 2 ln by 60 into hs plus HD. In the earlier case, work done per second equation was rho g ln by 60 into hs plus HD. Here also the work done per second is just doubled. Okay, if once we can calculate the work done per second, now directly dividing by 1000 we will get the power or work done per second in terms of kilowatt. That is the expression for work done. That is the expression for power. Okay. So in a simple way, what you have to remember is, in this case of single acting pump, if D is neglected, in the case of single acting pump, the Q equation is ALN by 60. Here it is 2 ALN by 60 if D is neglected. In the case of single acting pump, equation for work done per second is rho g ALN by 60 into hs plus HD. Here it is rho g into 2 ALN by 60 into hs plus HD. Factor of 2 is multiplied in the both the equation to get the discharge and work done per second in the case of the double acting pump. If the D is considered, or we cannot neglect the value of D, or in the problems and all, if the value of D is given, then you have to consider the value of D, then the above these two equations are to be used. That is discharge equal to pi by 4 d square plus pi by 4 d square minus d square into L into n by 60, and work done per second equal to rho g into pi by 4 d square plus pi by 4 d square minus small d square into L into n by 60 into hs plus hd. The instead of writing a 2a, what comes is a plus a1. Remember that equation. In that way you can remember it, I think. Now next topic is slip of the reciprocating pump. Slip of a pump is defined as the difference between the theoretical discharge and the actual discharge of the pump. This term is usually known as the slip of the pump. Mathematically, slip is equal to Q theoretical minus Q actual. As we all know, in the most of the practical cases, theoretical value will be always greater than the actual value. Theoretical is nothing but the discharge calculated from the using the equations. Single acting pump ALN by 60. In the case of double acting pump, it is 2 ALN by 60. Actually, is something that we are obtaining from the practical calculation. Some tank is being provided, and with respect to time, how much water is collected, we can calculate Q actual. So actual will be always given in the question. Theoretical we can calculate with the equation. So usual cases and all, theoretical will be always greater than actual discharge. And sometimes the slip is also expressed in terms of its percentage value, and it's given as Q theoretical minus Q actual divided by Q theoretical into 100%. Remember, Q theoretical minus Q actual, higher value minus lower value divided by the higher value. That is the equation, Q theoretical minus Q actual divided by Q theoretical into 100%. But we all know from the fluid mechanics, Q actual by Q theoretical is nothing but coefficient of discharge. So this equation can be rearranged as 1 minus Q actual by Q theoretical 1 minus Q actual by Q theoretical into 100%. That is equal to 1 minus CD into 100%. Sometimes in the problems and all, CD value will be given instead of Q actual by Q theoretical. In that case, you can directly calculate the percentage of slip as 1 minus CD into 100. And care should be there. If slip is supposed to calculate, then you have to calculate slip as Q theoretical minus Q actual. That difference only. It will have some unit, that is meter cube per second. But in the case of the percentage slip, it won't have any unit. It will be in the percent. It will be in the value of percentage, like 60%, 70%, like that. Okay, where CD is the coefficient of discharge. Now, sometimes in the case of the reciprocating pump, there is a possibility of slip to be negative. Negative slip, as I discussed, slip becomes negative when actual discharge becomes greater than the theoretical discharge. So in that case, the possibility of slip is there to be negative. The reason for the negative slip to occur is when the delivery pipe is short and suction pipe is long and the pump is running at a very high speed. This is the possibility of negative slip to occur.